Okay, so Bismillah Rahman Rahim. Today is lecture number 6 and 7 of the course Irrigation Engineering. In today's lecture, we will study about the design of irrigation canals. We will continue with the Kennedy's silt theory. We will study about the Lacey's regime theory. We will study about canal lining, and we will also study about the maintenance of irrigation canals. Now, Kennedy's silt theory, we started in the previous lecture. So, Kennedy did not give any equation for slope of canal. The slope is decided according to the ground available. So, in his theory, Kennedy did not give any equation to calculate the longitudinal slope of the canal. So the slope is decided according to the ground available. From the plotted longitudinal slope of the alignment, there is always a certain range of slope that can be given to the channel at the side. Just like you remember from the profile leveling of the road in your survey came. So there, if you remember, there was a certain range of slopes for the alignment. So similarly, for the case of a canal, from the plotted longitudinal slope of the alignment, there is always a certain range of slope that can be given to the channel at the side. For every such slope, a separate channel can be designed to suit a given discharge. So if we change the slope value, a separate channel dimensions can be obtained for the given discharge. For example, we consider the discharge of 2 cubic meter per second. This is the rugosity coefficient. M is the critical velocity ratio. So we get the following dimensions for various slopes. You can see here that if we consider the longitudinal slope of the canal is 1 in 5,000, so the bottom width of the channel, that is 7 meter, and the depth of water, that is 0.68 meter, giving the ratio B by D is 10.8. Similarly, if we consider the slope is 1 in 4,000, in that case, the bottom width of the channel, that is 3.2 meter. The depth of water is 0.85 meter, giving the B by D ratio is 3.8. And for 1 in 2000, the B value is 1.5 meter, the depth is 1.4 meter, and the B by D ratio, that is 1.07. Now you can see that if we consider the different slopes, we get different dimensions of the channel for the same discharge. Rugosity coefficient and critical velocity ratio. Unfortunately, Kennedy's theory provides no clue to which of the channels will be best suited for a particular discharge and type of soil. Now in this case, you see that these are the dimensions of the channel for the discharge of 2 cubics. So Kennedy's theory does not provide any clue which of the channel sections that will be best suited. Clear? Hence, some guidance is necessary to find out which channel would suit the need best. To provide this guidance, suitable B by D ratios were fixed in various departments on the basis of experience. So in order to provide some guidance that which channel would suit the need best, suitable B by D ratios, these were fixed based on the experience. Wood's normal design table, which you can find in the book Irrigation and Water Power Engineering by Pumia, is one such criteria which was prepared in Punjab and is very much in use. Thus, if B by D ratio is selected from the recommended values, one more equation is available. Hence, unique design of a channel can be done, including the bed slope using Kennedy's theory. So if B by D ratio is selected, then one more equation is available and we can have a unique design of the channel, including the bed slope using Kennedy's theory. So we have case number 2, when discharge rugosity coefficient, critical velocity ratio and B by D are given. So we have a step-by-step procedure. So step number 1 is calculate the area A in terms of D. Because B by D is given, this will be given, this ratio is given. So from here we have B is equal to D times X. Now we have this area equation for the trapezoidal channel. So if we take the side slope as half to 1, this is the trapezoidal channel here. So this is the depth for the design discharge, and this is the width, the bottom width of the channel. So we have this equation. Now in this equation for area, we replace a B here. So replace the B. Now area is equal to D square into X plus 0.5. Considering these as the side slope. Clear? This is Z21. Now step number 2 is the value of V is known in terms of D by Kennedy's equation. So this is the equation here. The critical velocity that is given by the Kennedy's equation. So substitute the values of V and A in the continuity equation and solve for D. Now we have this as the area, that is in terms of the depth of water, and this is the velocity equation in terms of the depth of the water. So we have continuity equation Q is equal to AV. This is the continuity equation. So just we put the value of A from this equation, and this is the velocity value coming from the Kennedy's equation. Discharge is given to us. So we can simplify this to calculate the value of D. You see that in this equation, discharge is known, the critical velocity ratio that is given, X is given, this is B by D ratio. So this is given. So depth of water, it can be determined. Step number 3 is that now we have calculated the depth of water, so we can calculate the bottom width of the channel. Because this B by D ratio is given, now depth is known, we can easily calculate this B. And when the depth of water and the bottom width of the channel are known, we can calculate the hydraulic radius. So using this equation, we can calculate the bottom width of the channel, and now B and D are known, so we can calculate the hydraulic radius. Calculate the velocity V from Kennedy's equation. Now that depth is known, so in this equation we can put the depth of water, so we can calculate the critical velocity. Step number 5 is knowing the velocity and the hydraulic radius. We can determine the slope, longitudinal slope of the channel from the Chazy and Cutter equation. So this is the Chazy Cutter equation. You can see here that the Chazy formula is V is equal to C into square root of RS. So we replace this by C by the Cutter equation. So this is actually C here coming from the Cutter equation into square root of RS. This is in MKS system. Now in this case you can see that the S, the slope that is present in the numerator and the denominator. Now since S is present in the numerator and the denominator, this equation can be solved by trial and error. Now for this case too, let us try to solve a problem, how we apply this step-by-step procedure to design an irrigation canal with the following data by Kennedy's theory. Given the discharge is 14 cubics, rugosity coefficient N, that is 0.0225, critical velocity ratio is 1, and B by D ratio, that is 5.7. So we have this step-by-step procedure. We go for step number 1. We are given B by D ratio, that is 5.7, so now from here we get B is equal to 5.7 times D. Now we have the equation for the area. So area is equal to B times D plus D square by 2. And this is for side slope Z ratio 1, that is equal to half half ratio 1. Now in this equation you can see that we have this area A, so we just put B is equal to 5.7. This we can take out this D square as common, so this will be equal to B by D plus 0.5. Now this B by D is given to us. This is 5.7 plus 0.5. So from here area A, this is equal to 6.2 D square. This is now the area. Step number 2 is we have the critical velocity in terms of depth of flow. So this is equal to 0.55 m into d power 0.64. Now in this equation m that is given as 1, so this will be equal to 0.55 into d power 0.64. Now we have this Q is equal to AV So A is equal to 6.2 into D square and velocity is equal to 0.55 Now you can see that discharge is given 14 cubics, and in this equation the only unknown is a D. So we can calculate the value of a D. So D will be equal to a discharge divided by 6.2 into 0.55 Now you can see here we have D power 2 and D power 0.64. So it will be 2.64, and then shifting to the other side it will be 1 divided by 2.64. So now solving from here, we will get the value of a D. So D comes out to be 1.71 meter. Now step number 3 is we can calculate bottom width of the channel. That will be equal to 5.7 times the depth. It is given here. So now the depth value we have already calculated above. So B will be equal to 9.75 meter. Similarly, we can calculate the hydraulic radius. So this is equal to area divided by the wetted perimeter. So this will be equal to B times D plus we have D square by 2 divided by the wetted perimeter, that is B plus D into square root of 5. This is for side slope half to 1. So now if you put the values, so R comes out to be 1.34 meter. Step number 4 is to calculate the velocity using the Kennedy's equation. So V is equal to 0.55 m into d power 0.64. So you can put the values m is equal to 1 and d we have calculated as 1.71 meter. So velocity comes out to be 0.775 meter per second. Now step number 5 is to calculate the slope S. We will use the Chesy-Manning formula. So you can see here that V, that is equal to 23 plus 1 by n, take care of the system of units, plus 0.00155 divided by S this whole divided by 1 plus 0.0 0.00155 divided by S into N divided by square root of R into RS square root. So now in this case you can see that the only unknown is S in the numerator and in the denominator. So solving by trial and error, so we will get S is equal to 1 divided by 4940. So you can see here that by considering the B by D ratio, we have a unique solution as per the Kennedy's theory. So drawbacks in Kennedy's theory: Kennedy did not realize the importance of B by D ratio. You see that we already discussed this B by D ratio, that this provides the guidance, because for the different slopes we get the different cross sections for the same discharge. Here you can see that. So that is why some guidance is necessary, that for the given discharge which channel that will be best suited. So for this purpose what happened is that suitable B by D ratios, they were fixed based on the experience. In this case, this table which is given in the book Irrigation and Water Power Engineering by Pumia, you can find this table. This was one such criteria. Clear? So by fixing this B by D ratio from the recommended values, one more equation is available, and we have unique design of the channel including the bed slope. So Kennedy did not realize the importance of B by D ratio. He did not define the silt grade and the silt charge. He did not give any relation between the velocity of flow and the water surface slope. Empirical relations between velocity, depth, hydraulic radius, and the slopes were found to determine a stable cross section. So it means that when you have empirical relations, it means that those equations are applicable to similar conditions. If conditions are other than that for which these equations are developed, So then it will not be appropriate to use those relationships. He did not give any relation for the bed slope of the canal. The bed slope could be adopted as per ground condition. He did not account for silt concentration and bed load separately. He accounted all factors in one single factor m, critical velocity ratio. For the design of a canal, he aimed to achieve the average regime condition. And for the determination of mean velocity of flow, he solely depend upon the Cutter's equation. Thus, the limitations of Cutter equation were incorporated in his theory also. So, these are the drawbacks in the Kennedy's theory. So, next we study about the Lacey's regime theory. Lacey, an eminent civil engineer of UP, United Provinces Irrigation Department, published his first paper through the Institution of Civil Engineers, London in 1929. He carried out extensive investigations on the design of stable channels in alluvium. On the basis of his research work, he found many drawbacks in Kennedy's theory. It was stated by Kennedy that a channel is said to be in a state of regime if there is neither silting nor covering in the channel. So Kennedy said that a channel will be in a regime that will be stable channel if there is non-silting and non-covering in that channel. But according to Lacey, even though a channel with no silting and no covering may actually not be in regime. Lacey therefore differentiated between three regime conditions: true regime, initial regime, and final regime. So, regime conditions. A channel is said to be in a regime when the following conditions are satisfied. Number one, channel is flowing in unlimited incoherent alluvium of the same character as that transported. What we mean by incoherent alluvium? So, incoherent alluvium means loose granular material which can be scoured out as easily as it is a deposit. Incoherent alluvium is loose granular material which can be scoured out as easily as it is transported. So the first requirement is that the channel is flowing in unlimited incoherent alluvium of the same character as that transported. Discharge is constant. Silt charge is constant, that is the amount of silt is constant. Silt grade, silt size, that is constant. And flow is uniform. So a designed channel is said to be in true regime if the above conditions are satisfied. If these conditions are satisfied, then the channel is said to be in true regime. But in practice, all these conditions can never be satisfied and therefore artificial channels can never be in true regime. Hence, Lacey gave the idea of initial and final regime for actual channel. You see that the above conditions, if these are satisfied, then the channel is said to be in true regime. So in practice, these conditions can never be satisfied in artificial channels, clear, that we design. So that is why artificial channels can never be in true regime. So Lacey give the idea of initial and final regime. So what we mean by initial regime and final regime? Initial regime, one of the conditions of attaining a regime of a channel is that there should be freedom for the channel to form its own section. A channel, it should form its own section, clear? Section means the cross section of the channel. Initial regime is the state of channel that has formed its section only and yet not secured the longitudinal slope. What we mean by the initial regime, that the bed slope of channel varies, the cross section or wetted perimeter remains unaffected. So these are the conditions for the initial regime. The bed slope of the channel varies. And why the bed slope of the channel will vary? If the channel is constructed in defective slope, so it will try to adjust its slope. So initial regime is the state of the channel that has formed its section only and yet not secured the longitudinal slope. Final regime, if all the variables such as perimeter, depth, slope, etc. are equally free to change and finally get adjusted according to discharge and silt grade, then the channel is said to have achieved permanent stability. And this is known as final regime. All the variables such as the perimeter, depth, slope, etc. are equally free to vary. The channel is said to have achieved permanent stability called final regime. So regime theory is applicable to such channels only. Such a channel in which all variables are equally free to vary has a tendency to assume a semi-elliptical section. This is according to this Lacey regime theory. This is what the Lacey regime theory says, that in a channel, if all variables are equally free to vary, this is because we have unlined channels, clear? So such a channel in which variables are equally free to vary, you see we have unlined channels, so there will be tendency of silting and scouring. So in that context, such a channel in which all variables are equally free to vary has a tendency to assume a semi-elliptical section. So now it means that according to the Lacey's regime theory, the channels should form, or the channels have a tendency to assume a semi-elliptical section. This is according to this theory. The coarser the silt, the flatter is the semi-ellipse. You can see here that this is the channel shape carrying coarse silt. What will happen if we have coarser silt? So the channel will be having narrow depth, clear, or you can say shallow depth, and wide. That is, greater is the width of the water surface. The finer the silt, the more nearly the section attains a semicircle. So if the channel shape is this one here, it is narrower but deeper. Depth is more here, and it becomes narrower. So channel shape carrying fine silt. This is what is according to this theory. The second point which Lacey argued was that sediment is kept in suspension not only by the vertical component of the eddies which are generated on the channel bed, but also by the eddies generated on the sides of the channel. You see, Lacey argued that the silt supporting power of the channel is proportional to the wetted perimeter and not to its width as presumed by Kennedy. You see, we earlier studied in the previous lecture in Kennedy's theory. So Kennedy argued that the eddies which are generated at the bed of the channel, and these eddies are generated due to the friction the water is flowing. So due to the friction, these eddies are generated, and these eddies are responsible to keep the silt in suspension. So Kennedy said that there can be eddies from the sides, but for most of the part they are horizontal, and they contribute very little. So according to Kennedy, the silt transporting power that was proportional to the width. But Lacey argued that the silt supporting power of the channel is proportional to the wetted perimeter. According to Lacey, that the eddies which are generated from the bed of the channel as well as from the sides of the channel, they are responsible to keep the silt, the sediments in suspension. So according to Lacey, the silt supporting power of a channel that is proportional to the wetted perimeter and not to its width as presumed by Kennedy. Thirdly, Lacey argued that the grain size of the material forming the channel is an important factor and needs more attention. That was given by Kennedy different values of critical velocity ratio for different types of soils. Lacey therefore introduced a term called silt factor in his equation and connected it to the average particle. Next, we defined the permanent regime. A channel is in permanent regime when its section is provided with a lining to protect against the covering action, thereby imparting permanency to the channel section and longitudinal slope. So a channel is in permanent regime when its section is provided with a lining to protect against covering action, thereby imparting permanency to the channel section and longitudinal slope. So this is the case when we have the lined channels. Clear? So regime theory is not applicable to such channels. That's why we apply these Kennedy and Lacy theories to unlined canals. Now, the design procedure involves no trial and error procedure. For the channel design, as per the Lacy's regime theory, the discharge and the mean diameter of the silt particle, that is d sub mm. This represents the mean diameter of the particles in millimeter, or silt factor f should be known. This data should be known. Then we can follow the design procedure for the canals as per the Lacy's regime theory. So again, we have step-by-step procedure. So step number 1 is to calculate the silt factor. And this is the equation which relates the silt factor with the mean diameter of the silt particles. This d sub mm, that is the mean particle size in millimeter. Step number 2 is that we will calculate the velocity v. So the velocity equation, this is in MKS system, and this is the equation to calculate the velocity in the FPS system. Now you can see here that these equations where v is related to the discharge and the silt factor, these equations can be developed. Clear? You can read in the book, but no need to derive or develop these equations here. Clear? So these equations, we will be able to calculate the velocity. Now the discharge is given and the velocity is calculated here. We can calculate the cross-sectional area of the channel by dividing the discharge by the velocity. Step number 4 is to calculate the wetted perimeter. For wetted perimeter, these are the equations given by the Lacy's theory in the MKS system and in the FPS system. Now, find out, step number 5 is to find out the bed width B and the depth D of the channel section, since area A and P are known. So in step number 3, we have calculated the area A, and in step number 4, we have calculated the wetted perimeter. So now we can calculate the bottom width of the channel and the depth. If we assume a side slope half to 1, then these are the equations for the area A and the wetted perimeter P. Remember, if in a question the side slopes are different, don't use these equations, because these are simplified equations for this side slope. If the side slope is different, then these equations should not be used. Now in this equation, you can see that a D will be given by this expression here. We just simplify these equations. You see here area A and the wetted perimeter. So we can calculate the value of the depth of the cross section, and from here put the value of P and D, so we can calculate the bottom width of the channel cross section. Step number 6 is to calculate the hydraulic radius. Hydraulic radius is area divided by the wetted perimeter. But as per the Lacey's theory, he gave this equation here for the hydraulic radius. Now we will calculate the hydraulic radius from this equation, but we can also calculate the hydraulic radius from this equation, area divided by the wetted perimeter. And these two values should agree. So this will provide as a check on the calculations. These two values should agree. This will provide a numerical check on the calculations. So both the values of R should be the same. This will provide a numerical check from step number 1 to 5. And step number 7 is find the slope S. Again, Lacey's theory gave equation to calculate the longitudinal slope of the channel. So these are the equations for calculating the slope in MKS system and in the FPS system. Now, this table gives the value of particle size for various types of alluvial materials. For example, we have silt, so very fine, 0.05 to 0.08 millimeter. Fine silt, 0.12 millimeter, medium 0.16, and standard silt, so that is 0.32, for which the silt factor is 1. Similarly, we can have for sand, gravel, boulders. So if in the problem this average size or the type of material is given, this table can be used to know about the average grain size, and this can be used to calculate the silt factor. Let us try to solve a problem. Design an unlined channel as per Lacey's theory. The discharge is 30 cubic meter per second, 30 cumics. The mean diameter of silt particle, that is 0.33 millimeter, and the side slope, that is half to 1. So as we discussed, again we have a step-by-step procedure. So let us try to design this unlined channel using Lacey's theory. So we have step number 1. We will calculate the silt factor. Now for this we have the formula, this F, that is equal to 1.76 into square root of D sub mm. So just you can put here this 0.33 here. So this will come out to be 1.0 something, so 1. Now step number 2 is we calculate the velocity. So for the velocity, we have the equation V is equal to Q F square divided by 140. Take care of the system of units into power 1 by 6. So now discharge is given and F is calculated in step number 1. So this V, it comes out to be 0.773. 0.773 meter per second. Next, we have to calculate the area A, that is step number 3. So velocity we have calculated in step number 2, discharge is given. So area A, that will be equal to discharge divided by velocity V. So discharge is 30 divided by 0.773. So area comes out to be 38.81 square meter. Now next we can calculate step number 4. We can calculate the wetted perimeter, and for the wetted perimeter the formula is 4.75 into square root of a discharge. So just put the values for discharge, 30 cubic meter per second. This comes out to be 26.02 meter. Step number 5 is now to calculate the bottom width and the depth. So for that we have to calculate the bottom width and the depth. So the formula for the depth, and we are assuming the side slope is half to 1, remember. So for that, then we have the formula is equal to P minus square root of P square. P is the wetted perimeter, minus 6.944 into area A, this is A, divided by 3.472. So just put the values. This here, this formula we are using. So the value of D comes out to be 1.68 meter. And now we can calculate the bottom width of the channel cross section, that is equal to P minus 2.236 into a D. So this comes out to be 22.26 meter. Step number 6 is to calculate the slope. So for this, before we calculate the slope, actually we need to calculate the hydraulic radius. So step number 6 is to calculate the hydraulic radius, and we have this R, that is equal to 5 by 2 V square by F. So just put the values. This R comes out to be 1.49 meter. Now to apply a check, we can also calculate the hydraulic radius. This is just to check the calculations. So we already know that hydraulic radius R, that is equal to area divided by the wetted perimeter. So for the given side slope, this equation is equal to B times a D plus a D square by 2 for area, and for the wetted perimeter, this is equal to B plus a D into square root of 5. So if you put the values, this comes out to be 1.49 meter. So this is 1.49 meter and this is 1.49 meter. Clear? So this is check on the calculations. And step number 7 is to calculate the slope. Now for the slope, we have equation as given by the Lacy theory. S is equal to F 5 by 3 power divided by 3340 into Q power 1 by 6. So if you put the values, this S comes out to be 1 divided by 5900. This is the longitudinal slope. Next, we discuss drawbacks in Lacey's regime theory. You see, the concept of true regime is only theoretical and cannot be achieved practically. The various equations are derived by considering the silt factor, of which is not at all constant. You can see here the various equations. For the slope, it is related to this f. You can see here that we have this velocity here that is related to this f. So the various equations are derived by considering the silt factor, of which is not at all constant. The concentration of silt is not taken into account. The silt grade, size, and the silt charge, the load, are not clearly defined. The equations are empirical and based on available data from a particular type of channel. The characteristics of regime of channel may not be same for all cases. So these are the drawbacks in the Lacey's regime theory. But no doubt this Lacey's theory was more popularly used as compared to Kennedy's theory in the subcontinent. Next, we discuss the comparison of Kennedy and Lacey's theory. So you can see that Kennedy's theory states that silt carried by the flowing water is kept in suspension by the vertical component of eddies which are generated from the bed of the channel. Lacey theory states that silt carried by the flowing water is kept in suspension by the vertical component of eddies which are generated from the entire wetted perimeter of the channel. So we already discussed this. Kennedy's theory gives relation between V and D, the critical velocity. Lacey theory gives the relationship between V and R. If I go back, see the equation for V. So this equation is not written here, but the Lacey theory, it gives the relation between V and R. Clear? So it is actually written here. If I go back, so you can see here, this is here V and R. Number 3, critical velocity ratio is introduced to make the equation applicable to different channels with different silt grades. In Lacey's theory, silt factor F is introduced to make the equation applicable to different channels with different silt grades. Cutter's equation is used for finding the mean velocity, whereas Lacey theory gave an equation for finding the mean velocity. Kennedy theory gives no equation for bed slope of the channel. Lacey theory gives an equation for the bed slope. Kennedy's theory for design of unlined canal, that is based on trial and error method. The Lacey theory does not involve trial and error method.